You can bring all the ones that you used during class, the test, plus an additional one. All right, let's share my screen. All right. Okay, so we're gonna continue with complex eigenvalues and eigenvectors. So we looked at this where you have a matrix that's, depends on what kind of A matrix you have. You may have a characteristic equation for lambda, which is going to be a quadratic equation. And of course, quadratic equations can either have distinct real, repeated real, or complex. We're going to skip the repeated real. But if you have complex, like 1 plus or minus I, the way you find the eigenvectors are still the same. You just plug in 1 plus I as one of the eigenvalues. And then you can use either the first or second equation. They're going to be equivalent. You're going to get a relationship between U and V that may have I still in it. So in this case, U is equal to IV. You can say V is some C1, it's a free variable, but U better be I C1 at that point. And then the eigenvector is the vector UV. And so you plug those in, you can factor out the C1. And so you have an eigenvector that has imaginary in it. And the other eigenvalue is the complex conjugate. It's going to be the I minus or 1 minus I. Plug that in. The idea is still very similar, just that the fact that this is now a minus I instead of plus I results in a relationship between U and V that's very not unexpected, right? U is equal to negative IV instead of positive IV. And so you just have the same pretty much eigenvector, but the I just became negative I instead. That's due to the fact that this plus I became a minus I. And so this will always be true. Your quadratic equation, when it has complex roots, will be in conjugate pairs. Their eigenvectors will also be in conjugate pairs, which means that anytime you see I, the other one will be negative I. And this is always true due to this proof. So if you have eigenvalues that are complex conjugates, so that means lambda is alpha plus or minus I beta, and then let's say you found the eigenvectors for that, which is by just plugging in the lambda 1 here, and then you're trying to find the V1s that do that. So let's say you find an eigenvector V1 that does satisfy this equation. Let's suppose you take that and take the complex conjugate of both sides. The A matrix is all real. In our class, they'll all be like all actual real numbers, like 1, -1, 1, they're real. Complex conjugate of a real matrix is itself, because there's no imaginary part. But then you can put this bar just means complex conjugate. So then the complex conjugate of A vector V1 would just be the matrix A times the complex conjugate of V1. And then the right-hand side would be the complex conjugate of both of these. We just said that the eigenvalues occur in conjugate pairs. So the complex conjugate of lambda 1 is lambda 2, because lambda 2 is the complex conjugate of the other eigenvalue. So we could replace that, make that replacement of lambda 2 is equal to the complex conjugate of lambda 1. So you have A complex conjugate of V1 is equal to lambda 2 complex conjugate of V1. Well, this is the complex conjugate of V1 is exactly the vector that satisfies this eigenvector equation with eigenvalue equal to lambda 2. So therefore, this must be the second eigenvector. And so this means that, V1 complex conjugate has to be V2. Okay, so this is just a proof. We just saw one example where we saw that the eigenvalues being complex conjugate results in eigenvectors being complex conjugate. That's not a proof because that just shows you one example. It might have been a coincidence, but it'll always be true because this analysis is not giving you any particular lambda 1s or lambda 2s. They're leaving everything in general. And it shows that the conclusion is V2, the eigenvector V2 must have been the complex conjugate of V1. Okay, so that's that. So the punchline is, so once you have your two complex conjugate eigenvalues and the eigenvectors, that means that you can write your eigenvalues as the real plus or minus the imaginary part. The vectors themselves can actually be split into the real vector and the imaginary part. We'll see how to do that in a moment. But once you're able to split the real and imaginary part for both the eigenvalues and the eigenvectors, then you can put those in these spots right here. This is the actual full vector solution to the system of equations when you have complex conjugate eigenvalues. How do I get this? This is the real solution. How would I get this? That is stuff that I just went ahead and posted ahead of time here. I'll probably step through this really quickly, but it's the same thing we've been always doing. You have to use Euler's formula to be able to rewrite your solution, which in general before we saw was just the e to the lambda 1t times the first eigenvector plus the e to the second eigenvalue times t plus times the second eigenvector. You could actually take this in the case that you have complex conjugate eigenvalues and then apply Euler's formula, consolidate the real and imaginary parts, and then you'll get this final formula right here. But let's just see how we'll use this final formula with the solution we had before. So let's just see if, I think it's the same problem, yeah, 1, -1, 1, 1. Okay, so what did we get before? We got this result before. So let me just copy and paste this. How do we write the solution to this system? Let's just copy this. Okay, so what I'm going to do is I'm just going to point out that there is a V. I'll just do this. I'll just say V1. Whoops. The first eigenvector was equal to the C1 I1, and this was for lambda equal to, I'll just copy and paste. This was for lambda equal to 1 plus I. This is one of them, so I can delete this one now. And then the other one I'm going to list right here was C2 is -I1, and this was for when lambda 2 was equal to oops, 1 minus I. Okay, so then how do I, so you've got to extract the real and imaginary parts. So the lambda 1 and lambda 2 are complex conjugate. One is 1 plus I and the other one's 1 minus I. That one's easy probably to extract the real and imaginary parts. Lambda 1 and 2 are just plus or minus I, 1 plus or minus I. So that means that your alpha is equal to 1 and your beta is also equal to 1. That's the real and imaginary parts for your complex eigenvalue. Now, how do I split the eigenvector into its real and imaginary parts? You have to think about how can you add two vectors such that they add up to I1, and you got to extract what's the real part. There's a vector that's the real part plus I times the imaginary part. Does anybody want to share maybe what they think the real part of this vector would be?
0.
Good. 0, 1. And the imaginary part?
0.
1, 0. If you think about this, they add up to I1, right? So this is what it means to extract the real and imaginary parts. And in the formula we had up here, I'm saying V1, V2, the real part is vector A and the imaginary part is vector B. So when you do this, this is your vector A, the real part of the eigenvector, and this is the imaginary part of the eigenvector. So that's how you split. And so here, it's also consistent with this one right here. So with this one right here, here's what I'm going to write here. I'm just going to say, okay, so I'll just write here and just say 1, 1, 2, vector 1, 2 is going to be 0, 1 plus or minus I, 1, 0. Okay, and of course we just said here that vector A is this one, and vector B is this part is the image. So it's enough to just look at one of them, but this one is gonna be the other one. So this is going to be like the real part is 0, 1 minus I 1, 0. So it's consistent with sort of, if you look at this, this was like I plus I 1 plus I. This one's the one that's vector A plus I, vector B. This one's minus here, and this one's minus here. And so they occur in conjugate pairs. But the actual real part and imaginary part are 1 and 1. Just be careful here. So alpha is equal to 1 for both of these. That's clear. But beta is equal to 1 for both of these two. Even though this one's a plus I and this one's a minus I, the beta is still, like, if you see this, it's 1 plus or minus I. Beta is still 1. Sometimes, there's a confusion and they think, okay, beta is equal to -1. I mean, you could do that, but then you have to be consistent and have your vector B would have to be -1, 0. So the imaginary part of this is 1. If real part is 1, and then the imaginary part is 1. Even though there's a minus here, there's a plus here. That's how it works here. The same idea. So you have vector A is your real part, and the vector B is your imaginary part. And then this is the copy of the formula for the solution. So you just have to put it in the spots. So it's going to be like the solution vector X is going to equal C1 e to the alpha is 1, so e to the t, times the vector 0, 1. That's your A vector. Sine of beta is 1, so it's t. And then plus your B vector is 1, 0. Cosine of beta is 1, so that's t. C2 e to the t. The A vector is 0, 1. Cosine of t minus the B vector 0, 1. Sine of t. This is the full solution. And if you actually wrote this out by noticing that here, the terms inside this parentheses here is just C1 e to the t cosine of t, sine of t, and then this one's C2 e to the t negative sine of t, cosine of t. And you could I guess you could even distribute the C1s and combine this together, and you'll get that this is e to the t times C1 cosine of t minus C2 sine of t. And then this will be C1 sine of t plus C2 cosine of t. Because keep in mind, this is like your XY solution. So this is a vector solution with two components, where the first and the second components are the X and Y solutions to this system of differential equations. Okay, so this is written in matrix form, but really they're two equations for X and Y here. And so the solution does, when it's written like this, where A and B are vectors, is equivalent to a vector with two components. First component being the X solution, the second component being the Y solution. So where in the world did I get this formula? That's here. So we start with what we know from before is that this is like, when we had distinct eigenvalues, real distinct, we said that it's going to be, like we said way before here, like somewhere earlier, we had written a formula for this right here. We wrote this, right? E to the lambda t vector v, e to the lambda 2t vector v. This is the general solution in vector form that we had before. But in the complex conjugate eigenvalue case, you could start with the same thing. It's this right here. But then your lambda 1, lambda 2 are alpha plus or minus I beta and alpha plus or minus I beta. That's just because they're conjugate pairs. So those show up here. And then you can do this property of exponentials and split this up. Notice that e to the alpha t is common between both of them. So you can factor that one out right here. And then you can say, well, now I just need to take this expression in here and then use Euler's formula. This is where Euler's formula is being used. You have this is equal to this once you use Euler's formula. And you have this is equal to this. I'll use different colors. So this one can be orange. So that's just using Euler's formula. And then The other thing that I also note is that the V1s and V2 we just saw before can be split into its real and imaginary parts, vector A, I, vector B. But we also know that they have to occur in conjugate pairs. So that means the other one, if we were able to extract the real and imaginary parts for V1 as a vector A plus I vector B, the V2 must have been the same thing with the minus. So that's what we end up getting. And then all you do now is you have to FOIL this because this has like, you know, A plus and cosine plus. You got to do first, outside, inside, last. And then, of course, keep in mind that when you have I vector B times I sine beta t, that becomes real because I times I is I squared, which is -1. So keeping that in mind, you can consolidate the real part and the imaginary part. And so you'll have your real part, which is this right here after you do that. And that's right here. And then your imaginary part, which is this right here. And that goes here, but has an I with in front of it because it's the imaginary part. You can redefine your C1 and C2 and the C1 minus C2 times I as new C1s and C2s. The book likes to define it with this one being C1 and this one being C2. And then that's it. You'll get the formula. Well, just keep in mind that here I just did Euler's formula on this thing that's in the asterisk, but there is this e to the alpha t that's also being multiplied in the front, so that you just have to remember to put that in there. And that's how you get it. I mean, you can go and look at this carefully. It's basically this step, the orange became this and the purple became this using Euler's formula, and then all of the rest is just algebra and consolidating the imaginary parts and redefining. This C1 and C2 that we redefined in these blue C1, C2 may in general be complex, but we can keep the solution real if we choose C1 and C2 to be real. Let's say you have initial conditions where they're real, then your C1 and C2 would be real. But you know, you don't have to ever, as you probably noticed, derive these formulas from scratch. You end up, I guess, at the end of the day, just copying this in your formula sheet, and then you just need to know. What you do need to know is being able to take your eigenvectors and extract the real and imaginary parts, because those have to go into the vector A and vector B. But you should, I mean, it'd be good for you to understand how that formula for the solution came from Euler's formula. The next step is to draw the phase portrait like we did with the real eigenvalue case. So let's look at how would we draw like exactly the one we just did. So let me just copy and paste. So we got this, right? So this is just the same, right? 1, -1, 1, 1. So I'm just saying, why don't we draw 1, -1, 1, 1? So we know the solution is this right here. So we're like, let's draw this. I'll just write it like this. We want to draw how this is the answer solution for X and Y. So the question is, how do we draw this on a phase portrait? So they're giving you a parameterized curve for in T for X and Y. You want to be able to draw this trajectory on a plot. So what I'll do is I'll highlight this in blue. Let's not worry about the E of T first. So all I did was took this C1, and I chose C1 and C2 to be just one. So let's look at like the specific look at when, because of course, you know, there's some initial conditions that, you know, you can plug in, you know, because when you have C1 and C2 just like that, you don't know, you can't plot that. But let's say you have a specific situation where you have initial conditions that cause C1 and C2 to both be equal to 1. Then it'll be like cosine of t minus sine t, and then sine t plus cosine of t. And then on Desmos, believe it or not, you could plot a parameterized curve like this, where you say cosine of t minus sine t, comma sine t plus cosine of t, and then it'll let you be able to let t range from 0 to whatever. I mean, 0 to 100 is just causing this to trace over itself over and over and over again. Turns out that this is going to be a circle, basically. So I wouldn't have known that without putting in Desmos, that this is actually tracing a circle. And so this is the blue. So I'll just say this blue part of the solution. is equal to this picture right here. Now, the question is, this E of t, what is it doing to each of your x and y coordinates as time goes forward, or like t goes higher? It's like if you think about what is the E of t causing your solution to become? So let's say you have some xy solution, and then you have an e to the t that's multiplied to that xy solution. You know how the xy without the E of t looks like? It's a circle. But then the E of t will cause this kind of effect. It's like all your coordinates, because this E of t is just going to get multiplied to each of these because it's just a scalar, is going to multiply your x and your y. And so intuitively, that's going to cause your x and y coordinates to both simultaneously, as t goes forward, do what? Exactly, it's going to grow. It's going to grow. And so both your x and y coordinates will not stay in the circle. They will start to go, x will grow as well as y will grow as t goes on. What kind of shape do you think that'll become intuitively? It's going to be a spiral, and it's going to spiral out or in? Out. Yeah, so that's what the E of t is going to do. It's going to spiral out as t goes to infinity. So I'll just say, so let's draw how that's going to look like. Now, there are a couple ways that I can actually draw a trajectory that spirals out. So you could say it's going to like this. The other way is it could look like this. So just draw it down here. So I'm drawing the arrows out because I know that as t goes on, we know this is wrong. So it's going to go out. So this is how the arrows should be. Because you can't have arrows going into each other. They have to be consistent. So they're going out. This one is also going out. But if you notice, they're not the same spiral. Why they're not the same spiral? This one's going counterclockwise out. This one's going clockwise out. So the question is, which one is it? And also it starts into the origin because I know I just said like as t goes to infinity, then both your x and y coordinates blow up. But if you make t go to negative infinity, then e raised to negative infinity is like 0. And so in the other direction, your x and y coordinates are shrinking into the origin. So that's why the picture is either of these two. Now, to decide which of these two spirals it will be, you want to use kind of what we did before about direction vectors. We know direction vectors tell you, like, your solutions have to be tangent and go in the direction of your direction vectors. So, you could plot the direction field, but basically this A matrix is telling you that dx over dy or dt is equal to x minus y. That's from 1 to the negative 1. And dy over dt is x plus y. So let's say you want to find the direction at 1, 0. You just plug in. So you say dy over dt, dx over dt, sorry. Dx over dt is equal to 1 minus 0, which is equal to 1. Dy over dt is equal to 1 plus 1, which is equal to 2. No, sorry, not 1 plus 1. It's 1 plus 0 because your y coordinate is 0. And then this is 1. So your direction vector at 1 should be pointing 1 unit to the right and 1 unit up. And so this, let's say this is like my 1 position. This, like halfway between here to here, is 1 right here. And that's how the vector should be, is just like going like this. Same idea here. Now, knowing that this is my direction vector at 1, 0, which is at like the coordinate 1, 0, which one is correct. The left one. Yeah, this one actually follows, the trajectory is actually tangent to it. And also not only tangent to it, but has the right direction with the direction vector. This is actually going against it. This is saying that like here, my solution trajectory should be every time you cross the x-axis, go from bottom to up. But these are every single time you cross the x-axis going in, downwards into the x-axis. So this is going against the direction vector. And so this is, let's say this is wrong. So the way it turns out when you actually try to find the solution, here's what I'll do is I'll just copy and paste. So when you're trying to find these, draw the face portrait for complex, the case this right here is your e to the t. Where did this e to the t come from? This e to the t came from right here, which is like coming from your alpha, and your alpha was 1 in this case, and that's why you had just e to the t. So the punchline is whenever your alpha, in this case is equal to 1, is greater than 0, then you will have an exponential growth going on to both your x and y coordinates. So it's a spiral. It spirals out. Actually, I'll just say it's an unstable spiral. Why did I call it an unstable spiral? Because unstable, you know, like I said, a stable equilibrium, stable node, those stable ones are the ones where any, you know, if you're close to the origin, you stay close to the origin. This one, clearly, if you're here at the, it just pushes you out, right? So that means it's unstable. So spiraling out is an unstable spiral. Now, if you had alpha, like e to the negative t here, yeah, e to the negative t, let's say alpha is equal to -1, then you're spiraling in, right? Because as t goes forward with e to the negative t, that means that you're going to be getting closer to the origin as you end up, you know, going forward in t. So it's really the sign on your, so maybe I'll have an example of that. Yeah, we have an example of that. So we'll do that in a moment here. So let's look at this case where you have, this is your A matrix. So you'll say, oh, I'm just going to compute the characteristic. So I'll say determinant of this, or I just do this. It'll be -1 minus lambda times -1 minus lambda. And then it's going to be the minus this, so it's be +4 and equal 0. You can go through the process of doing this, and I trust that you can figure out how to solve this quadratic equation. You'll get your lambda is equal to -1 plus or minus 2i. And what's nice about this is I don't even care about the eigenvectors. If I'm just trying to draw the phase portrait for a complex case, what I did tell you here was it really is about the alpha. So even, you know, without having to write, you know, what the full solution is, unless they ask you for it, but if they only want you to sketch the phase plane, I think it's easier just, what's the alpha here? Alpha is equal to -1, which is less than 0. So it's going to be a spiraling in because it's like kind of like this with e to the negative t instead. So it's going to spiral in. And then the only other thing I need to know is it's going to spiral in clockwise or counterclockwise. But how did we do that last time? We just computed a direction vector. So I'm just going to use the same direction, the vector at the same spot that we did before, which is 1, 0. You could translate this to, you know, this is in matrix form, but if you wrote it out, it's dx over dt is equal to -x minus y. And this is dy over dt is equal to 4x minus y. And so you get dx over dt is equal to -1 minus 0, which is equal to, -1. dy over dt is equal to 4 minus 0, which is equal to 4. So that means that whenever I'm at 1, 0, which let's say is halfway between here and here, I need to be going 1 unit to the left, but 4 units up. So it's going to be kind of a steeper, but it's going to still be in this direction. That's the direction vector. I need to draw a spiral. So here it's going to be a stable spiral because you have decay. So it's a spiral, stable spiral. I need to draw a stable spiral. So that's a spiral that goes in that also follows this direction vector. And that's going to make it where you have really only one way of drawing it. It's going to look kind of like this. So you can't draw in any other way than this if you have to go inwards and also follow this direction vector. And see how fast that is? So I think like when you're drawing complex face portraits for the complex case, it's a lot easier, I think, than the real one. Because remember the real one, you had to compute not just the eigenvalues, but the eigenvectors. And then you had to like draw those eigenvectors. And then if they're both like going in or going out, you have to think about like those purple lines bending certain ways and stuff. All of that's like skipped in this case. You don't even need to compute the eigenvectors. If you're just trying the phase portrait, you just need the real part of your eigenvalue. So you just solve a quadratic equation for lambda. You just read off the alpha. That tells you whether you're going in or out. And then you plot a direction vector, which is literally just plugging in a point into this dx over dt, dy over t. Draw that vector, and then now you just have to draw a spiral that goes through that direction vector in that particular shape with either going in or going out. So drawing a face portrait for complex requires literally just this. This is it. This is the level of work necessary. It's not that bad. So we looked at the case when alpha is equal to a positive number, which causes your, of course, your x and y coordinates to grow, and that's just unstable spiral. We looked at the case where it was negative, but we skipped one case. What case did we not look at? When alpha is equal to 0. So when alpha is equal to 0, well, then it would just be this blue piece, right? Because it'll be e raised to 0 times t. So it would just be this. This will be the plot for when alpha is equal to 0. When alpha is equal to 0, you don't have it spiraling in or out. It's just a circle, which is called an orbit. And it's called a stable orbit because it just will stay. It won't get blown away or anything. Alpha greater than 0, unstable. Alpha less than 0, stable. Alpha equal to 0 is a stable orbit. And so we can look at that case right here. So if you had like this system right here, and you wanted to compute the, so again, like this one, if you wanted to just extract the A matrix for this doesn't have an X, so it's 0, and then it's 1 for the Y, -1, 0. So then you can do the characteristic equation. The characteristic equation is going to equal basically negative lambda times negative lambda. And then you're going to have plus 1 equals 0. And of course, this is just going to equal lambda is plus or minus I. And that's pure imaginary because I wanted to look at the case where alpha is equal to 0. And then alpha is equal to 0. This is called a stable orbit, or actually, I think center is something that the book uses. So stable center or orbit, doesn't matter. It's stable because points that are nearby will stay in that orbit and not get blown away. And the way you're going to draw this, I guess I'll just say, okay, we'll just go down and say, okay, we know how this is going to look like. You have alpha is equal to 0. So it's a stable center. And I'm just going to write a direction vector right here. So direction vector, just write it down here. Direction vector at 1, 0. Again, like this is your dx over dt is equal to y. dy, maybe I'll just move it up so that we have dy over dx over dt is going to equal at 1, 0 is going to equal 0. dy over dt is going to equal -1. So your direction vector will be just going down, purely going down this. So your orbits are going to look like this. And there's actually infinitely many of these. They're just concentric circles. And so I can draw a few of them. Okay, and then the arrows on these ones have to follow the direction vector. All right, so that's a stable. And then why is it called a stable center is because points nearby the equilibrium, which is at the origin, will stay near it. They'll just stay as an orbit around it. So this is a stable center. That's all you need to be able to draw the phase portrait. So for the phase portrait, you just have to compute the eigenvalue, read the imaginary part. This one's pure imaginary, so there's no real part, so real part's 0. That's going to mean that doesn't spiral in or out. Now, I got to draw these orbits. How would I draw them? Well, they're just going to be circles like this. The only thing you need the direction vector for is to get the right arrow on them. And that's it, you're done. But let's just for review, say, let's compute the actual full solution to this. You don't have to for when you're, just drawing a phase portrait, but if you were to find the actual solution, then the same process we did earlier, where you just say, well, this is eigenvalues are plus or minus I. One of them is going to be positive I. So you could just plug it into the eigenvector eigenvalue equation, which is this. And this translates to this system. So I'll just say my A matrix is 0, 1, -1, 0. My eigenvector is UV. My eigenvalue is I, UV. You can use either of these two equations. So let's just use the first one. And so if you use the first one, you'll get that this is equal to 0 times U, 1 times V is equal to IU. In this case, maybe it's more convenient to just say U is equal to C1. Then if U, because I know I tended to say V is equal to arbitrary, it doesn't matter which one you choose to be the free. So U can be the free, then V must equal I C1. And then your eigenvector is built off of UV. And your U is C1 in this case, and your V is I C1. You can pull out the C1. It's 1I. And so that's your eigenvector. And the nice thing is I don't have to do the other one because I know that vector 2, eigenvector 2 is going to be C2 with what? Instead of 1I, it'll be every time you see an I, it becomes a negative I. 1 negative I. That's what it means to be a complex conjugate. So that's it. You don't have to do the work twice because with the complex case, they already know that they're going to be in conjugate pairs. The eigenvectors will be in conjugate pairs. So then how do we extract the real and imaginary parts? Let me just move this down. So what do we have? We have that vector 1 is 1I. Okay, so let's do that. So we have vector 1 is equal to C1 1I, and this was for lambda 1 is equal to I. And then the other one was C2, 1 negative I. And this was for lambda 2 is equal to negative I. And then the only thing you have to do is just extract the real and imaginary parts. So I'll just make it clear that our lambda was plus or minus I. So, right, this is what we had before up here, plus or minus I. So the alpha is 0 and your beta is 1. Now let's look at this vector. What's the real part plus the imaginary part? The real part is just 1, 0. The imaginary part is 0, 1. And you could do the same thing with this, but if you do do it here, you have to remember that this one's got a minus. So we have the full solution is equal to x of t is equal to c1 e to the alpha t, but that's just alpha 0, so e to the 0 is, I don't have to write that. And then it's going to be a sine of beta and b sine of both beta. Okay, so it's going to be a vector 0, 1 sine of t plus my b vector 0, 1 cosine of t. Was it sine first? Yeah, sine first. And then your other one's going to be C2, A cosine, B sine. Okay, so it's going to be your A matrix, the A vector sine. Was it sine? Cosine, sorry. So it'd be cosine T minus the B vector 0, 1 sine of T. Yeah, that's fine. So that would be the full solution to this if you were to write it out. Okay. And this was actually, we go back in time, the same as when we first talked about phase portraits, we had this example right here, right? This was dx over dt equals y, dy over dt equals x. So we had this in the past, and we just finally got to the point where we were able to actually see that the solution to this is equal to this, and we got it. And so I'll just paste it in here and just say that this is the same thing that we just did. This is dx over dt equals y, dy over dt equals negative x, dx over dt equals y, dy over dt equals negative x, and this is the full solution. If you wanted to, you could write out this whole thing. So you could say, if you multiply this out, this will end up being the same as C1 sine of t plus 0 cosine of t plus C2 cosine of t. The bottom is going to be C1 times 0, C1 times cosine of t plus C minus, because there's a minus here, C2 sine of t. And if you compare, let's see if I can fit this in one screen. If you compare this with this, they're the same. They're the same, but the C1s and C2s are switched. That's okay. You can label the C1 and C2 it doesn't matter how you label, but these are the same. And so I said, like back then, hey, this system, once we learn how to do complex eigenvalues, the solution will be this. But then I just said, let's wait. Let's just draw the direction field, and then eventually we'll be able to see that these are going to be stable centers that orbits like this. I do want to mention though that if you had say alpha is equal to 0, so you still have a stable spiral, but let's say you have a direction vector that looks like, I don't know, like a direction vector that looks like this, let's say. Okay, so the direction vector here was just purely down. So this is actually the right shape for the stable spiral. But for this one, it's not going to be a perfect circle anymore because you have to be tangent to this direction vector. So you're going to have, oh, no, you're going to have, well, it's not going to let me, I'll just do it like this. You're going to have ellipses like this. And so then the arrows are going to go like this. So just be careful that the direction vector for the stable spiral case will determine the shape of your spiral, not spirals, of your orbits. They have to be tangent to it. And so if it's like off like this, then it's going to be not a full perfect circle like this. This actually does capture the fact that this is the tangent here. It has to be purely down. But this is going to be, if you have a direction vectors that's not going purely up or down, you're gonna have to write not a spiral, it's an orbit that's gonna have to be in the shape of kind of like an ellipse in that case, to be faithful to the direction vector. So just keep that in mind. This is a very unique case where you had a direction vector that would correspond to a pure circle, but you might have something like this. So that's that. The next thing, so we have 3 class periods, and I have like basically a week worth of classes because 3 class periods. Because our Tuesday is our test, but it's because it's a Friday schedule, and so we have Wednesday, Friday, and Monday 3 class periods for me to do the last thing, which is Laplace transforms. So we'll do that starting on Wednesday. So have a good day.
Say so.